This conference will now be recorded.
Welcome everyone to Smpte Philadelphia's webinar with Peter Putman. Peter Putman is with ROAM. He's president of ROAM Consulting, and today he's going to talk to us about projection and direct view displays. How bright is too bright? And with that, I'm going to turn it over to you, Peter. Go ahead, stage is yours.
All right, I'd like to thank everybody for turning out. I know we have a small crowd today, but I think you're going to find this an interesting presentation. Some people ask me where I came up with this idea. As somebody who's been following the display industry for years and going to too many trade shows and seeing too many demos of the latest and greatest in display technology, I kind of wondered when we'd reach a point when displays would be bright enough. Well, we have reached that point. And now I'm starting to wonder if some of the display applications I've seen, some of the installations are too bright. If people are not using some common sense and saying, wait a minute, I don't need all that much light on the screen for what I'm doing. How about if I use just enough? And that brings up the question is, what is just enough? How do you know how much is enough? How do you know when it's too much? So let me set up my screen here. And we can rock and roll. Great. And let me minimize this. All right, so this is sort of a recap of a presentation I did at the HPA Tech Retreat, the virtual retreat earlier this year. So some of you have already seen it. I apologize. I don't think a lot of you did see it. So getting back to what I originally said, can a display be too bright? Well, absolutely. We got used to the fact that screens weren't bright enough for a long time. When we had CRTs, it was really hard to push them much past about 29-foot Lamberts, which was the Smpte standard for a CRT monitor, 100 candelas per square meter. And in fact, reference monitors for the longest time before high dynamic range came in were set to 100 candelas per square meter. So there's always that question about, was it that standard because that's as hard as we could push them? That came out of a bunch of studies done in the 80s on CRT monitors, and that seemed to be a target that everybody could hit. In the cinema, we're really hard pressed to maintain the Smpte target, the 16-foot Lamberts, or 55 candelas per square meter. You know, and when 3D came in, you had to put the glasses on, it got even darker. But that was then, this is now. We have televisions that can easily crank out 300 to 1,000 candelas per square meter. Some models are pushing 2,000. We have projectors that can deliver up to 50,000 lumens, which is a staggering amount of brightness. We have direct view LED displays that can achieve 3,000 and 4,000 candelas per meter squared, and the fine pitch displays is what I'm really focusing on. Typically, they peak out at around 3. So we have an abundance of lumens, and the question is, do we really need displays that are that bright? Well, the simple answer to that question is it depends on the application and the viewing environment. So sure, we walk through Times Square, we go down the Las Vegas Strip, and we see these. And these are extremely high levels of luminance, thousands of nits, especially in the daytime, but they're intended to grab your attention momentarily. You're not going to stand in front of these things for long periods of time viewing. First of all, one of those annoying characters is going to come up and try to get a selfie with you, and secondly, you might get run over by a car. But these guys are all competing with everything else that's going on in Times Square. So there's other LED signs, street lights, other high ambient levels. As a matter of fact, when you go into Times Square at night, it's almost lit up with stadium lighting. That's how bright it is. On the left, we have a projector that was shown in Infocom a few years ago, Panasonic's PT-RQ50KU. This is a 3-chip DLP, and this is an honest-to-God 50,000 lumens. Now, they've done projector mapping down at Disney for the Enchanted Castle, Sleeping Beauty Castle. They can light that whole thing up at night with this projector. And the one on the right is super bright because it's doing virtual reality in 3D, so it has to overcome polarization losses in the glasses. And you can feel the warmth coming off the screen. So really, how many photons are enough? Well, here's a demo at Samsung's executive demo center out near the airport in Irvine, California. And these are outdoor displays, and they're rated as high as 700 to 800 candelas per square meter, which is really, really bright. You wouldn't want to use these inside, but outside, again, you're competing with indirect or direct sunlight, cloudy, bright days, which is very common in California. So you need something like this. If you're working in a football stadium, then you need to really push it as hard as you can. So these are old pictures I took at Raven Stadium when they put in this wall, Sacco Smart Vision wall. Back in 1999, it was a 10mm pitch, which is really coarse nowadays, but it's fine for a stadium. It's rated at 4,000 candles per square meter. But keep in mind that the cloudy sky can be tens of thousands of nits, and of course the sun can be well over 100,000. So your shadows, even your deep shadows, can be hundreds of nits. So the question is then, all right, great, we can really crank up the firepower and we can dazzle people, and we can probably make them temporarily blind, but how much luminance do we really need, and how can we have too much luminance from a display? Now, to clarify, when we say bright, what we're really talking about is a visual perception metric. It's not even a metric, it's just that we're saying something's very bright. It appears bright to our eyes. So to be more accurate, let's focus on two ways of describing display deformance, luminance or illuminance. So luminance would be something like the moon or a projection screen. So it's light reflecting from a surface. Illuminance would be a projector or the sun, something that is illuminating a surface. And we measure luminance in foot lamberts, which is an English measurement, or candles per square meter. And it's very easy to go back and forth between the two of those. So if you know what the reading is in foot lamberts, you multiply by 3.1415, and you get, or 3.42 rather, and you get candles per square meter. And if you take candles per square meter, divide by 3.42, you get foot lamberts. Illuminance is typically measured in lumens, which is more of an English measurement, or lux, which is metric. So foot lamberts are candles per square meter to measure direct view display luminance, also light from projection screens. We use lux or lumens to measure light from projectors. So I'm going to kind of turn this whole argument on its side and say, let's stop worrying about how much illuminance or luminance we need. Let's figure just how much contrast do we need? Because really visual perception is keyed into contrast. What about the limiting contrast ratio? You can put as much light as you want on a screen, but at some point, a lot of that light's going to start lighting up the room because it's reflecting off other surfaces. So here's some useful industry rules that we've used in the AV industry to get us in the ballpark. So for passive viewing, just reading a book or a magazine, you need about 7:1. So if you're looking at dark text on a white background, about 7:1 minimum for comfortable reading. For a classroom meeting room presentation, about 15:1 is a good target. For analytical decision making, 50:1, and for immersive viewing, you want to be around 80:1 or better, which is, by the way, very hard to achieve. So these are not hard and fast rules, but they're targets. Now you're going to find that getting past 50:1 contrast ratio might require additional room treatments. So remember, calculating the contrast ratio customizes your installation, so you only pay for the luminance you need. It says LumiEmu. It's being smart. So let's see how this works. The black level in a room, otherwise the lowest light level, it's not really black, is set by ambient light. So if you're in a classroom or a meeting room and there's lights on, that's it. Whatever the brightest level in that room is, that's not on your screen, that's your ambient light level. That's basically your limiting black level. So your lumens target really should be the black level times the contrast ratio. And of course, lumens equals lux times the screen area in meters. So here's a typical example. We're in a classroom, take out a light meter, and we're measuring about 100 lux. Doesn't get any darker than that. We have a 16:10 screen that measures 120 inches diagonally, which is about 4.2 meters squared. So 100 lux times 4.2 meters is 417, 4.175, 417.5 lumens. This is basically our effective ambient black level. So our contrast ratio that we need is 15 times that. So 15 times 417.5 is 6262. So we can then, with confidence, say to our installer, we need a 6,000 lumens projector to light that screen up with a matte screen 1.0, which is unity gain, and get that 15:1 contrast ratio. Now, if we were to replace, to give you an idea of the crossover between the two measurements, if we were to replace the projector and screen with a one PC emissive display, we have about a 45-foot squared screen area. That would be about a 120-inch LCD OLED or inorganic LED display, which would be very heavy and very expensive. Now, 6,000 lumens on a 45 square foot screen is 133 foot lamberts, which is 455 candles per square meter. That's a very bright display. That's bordering on outdoor signage. But again, our limiting contrast ratio is only 15:1. So at 455 candles per meter squared, which is easy for a large LCD, or certainly easy for an inorganic LED display, that's comfortable. There's no eye strain looking at something like that at 15 to 1. But if we turn all the lights off in the room after a period of time, it could and generally does create visual fatigue after sustained viewing. So do you need high luminance if the room is dark enough? Well, let's find out. I ran some tests in my home theater. I have an old Mitsubishi H6000 3LCD projector, which I recently just replaced. No, it was not new in the year 2007. I have a typo there. 1,000 lumens full white is what it's rated. But after calibration, the measured output is much lower. It's 320 lumens. When I built this theater, I painted the walls with something called Sherwin-Williams Gray Matters. It's a neutral gray flat wall paint. It has a reflectivity of probably about 20%. So it's not that much above a gray card. The ceiling is satin white because when you're in the room and you need to see your way around, obviously you want to have a lot of light down there. So when we're working on music, we want it bright. The room lights are 4 600 candela per square meter warm white LEDs. So what I did was I got my spot meter out and I measured luminance from the screen and selected objects around the room, including the walls, footrests, and a shiny blue exercise ball. Then I calculated the ambient lumen contrast ratio from the results. Here's what it looks like. So there's 2 of the 4 lights. The walls are going to reflect some light, even though it's sort of a gray, neutral gray. Obviously, the glass in the picture reflects some light, but the chairs and pillows reflect light. That footstool reflects light. The blue light. And yes, my wife collectors all things. She's a collector of all things.
Peter, I'm going to interrupt you. Your microphone keeps dropping in and out. It's crackling.
Okay, then why don't we do this? How about now?
So far, that sounds a lot better.
Okay, I don't know why it's doing that. It could be because it's brushing against something.
Could be. Thank you.
Yeah, we'll just eliminate it. All right, where were we? So, assuming, whoop, I don't know why I did that. So here we are, we're back in the room. So I've identified all the spots in this room that are reflecting light. As you can see, the screen is kind of washed out. Now in each case, I'm not changing any brightness levels on the screen, any illuminance levels. It's a constant illuminance level. So let's drop half of the lights off right in front of the screen. Well, that improves things considerably. But we're still seeing reflection off the ball and off the chairs, off the penguins, off the footstools. So let's turn all the lights off. Well, now that seems plenty bright enough, okay? Except we're seeing some reflections off the ceiling. So what we've really done is improve the contrast ratio. So the full white pattern on the screen, what you're looking at is 50 candelas per square meter, all right? That's the Smpte target. Footrest measured 28, sidewall 21, the blue ball 18, the chair and pillow 32, the overhead light 600. So 50 candelas per square meter is 14.6 foot lamberts. Contrast ratio between the white and black squares on the screen with all the lights on is only 2.33 to 1. Between the white screen and the brightest object in the room is 1.6 to 1. Obviously, we have to drop the lights. We're looking at a projected image. So here, let's drop off these 2 front lights. Now what happens? Well, contrast ratio on the screen is better. Footrest is still kicking out about 2.5, the sidewall 1.9, the blue ball 2, and the chair pillow 4.3. Contrast ratio between white and black squares is now 14 to 1, which is better. It's not great. This is immersive. We want it to be really good. Between the white screen and the brightest object is 6 to 1. So when I drop all the lights off, I'm seeing contrast ratio changing now to 40 to 1, which is a heck of a lot better. It's not immersive, but it's halfway there. And now we're seeing 12.9 foot lamberts off the screen. Now, why did that number change? Let me back up 2 slides here. Well, part of the reason that we're seeing 50 candelas per square meter off the screen here and only 44 there is some of the light from those overhead lights in the front is spilling onto the screen. So right now, the projector's cranking out 44 candelas per square meter, 12.9 foot lamberts. We have a 40 to 1 contrast ratio. Yeah, it's probably okay for a home theater. It's not great. You can still see some stuff in the room. So I measured light output at the center of the screen with 100% white test pattern and a econic meter. Measure the contrast between white and black squares with Minolta CL200. So obviously, as we dropped the lights off, the contrast ratio between the brightest part of the screen and room ambient light increased considerably. Projected image appeared to get brighter as the lights were switched off, but I didn't change the luminance level. I didn't change the brightness level on the screen. Certain objects in the areas of the room reflected more light than others. So the 92-inch projection screen is 45 by 80. It's about 25 square feet. Happen to know that projector has about 84% uniformity. That's 2.32 square meters of screen area. And using the math I showed you before with a 9-point ANSI method, about 320 lumens of luminance. That's not much. Those of you who remember the old 9-inch Sony CRTs, they could put out about 300 lumens when they were calibrated. So this projector isn't really doing much better. 12.8 foot Lamberts, 44 candles per square meter is not a very bright projector, but it was bright enough for viewing. But I have no idea what the limiting contrast ratio is because of the limits on the econic meter sensitivity. So I hauled out a brighter projector, a BenQ W1500 I had sitting around. It's rated at 2200 white lumens, ran the same test patterns through it. Took the same luminance measurements, calculated the ambient contrast between white and black areas on the screen, and also the limiting contrast between the center of the full white screen, the brightest object in the room. So I ran the tests again. So here's full room lighting, 50% room lighting, now no room lighting. But you know what? Not a huge difference in the front of the room between 50% and no room lighting. There's still a lot of light bouncing off the ceiling, off the side walls, off the glass in those particular picture frames, off the projector itself, off the bolsters, off the footrests. So what did that do to our readings? Well, now we're seeing 210 candles per square meter off the center of the screen, 28 off the footrest, 24 off the sidewall, 18 off the blue ball, 32 off the chair and pillow, and 600 off the overhead lights, as we did before. We now have 61 foot Lamberts coming off the screen, but we only have a 7.8 to 1 contrast ratio between the black and the white squares, between the white screen and the brightest object, 6.6 to 1. So let's drop off those front lights. Now the contrast ratio between the white and black squares is better. It's 27.4 to 1. Between the white screen area and the brightest object is 34 to 1. That's still not immersive. So we dump all the room lights. Now we're at 47 to 1 between the white and black squares, and in the room we're at 51 to 1. So our contrast ratio didn't change substantially, even though we went to a brighter projector. And part of the reason is we're starting to see more reflected light off things in the room. Again, like the ceiling and like those lights that are off in my other projector and other stuff in the room. And we're at 52.3 foot Lamberts. So the BenQ projector is definitely brighter at 1300 lumens. That's after calibration, 52 foot Lamberts off the screen, but 51.1 limiting contrast between the brightest part of the screen to the darkest part of the room, which is a pretty bright room surface, is not good enough for immersive viewing. We have too many reflective surfaces in the room. We need darker paint, darker fabric, and also my cat was in there for a while, and I guess I need a darker cat, maybe a black cat. She reflects too much light. So there was a guy named Kim Milliken that I consider to be a genius in all things having to do with displays. Some of you have been in the industry a long time may remember he wrote something called the Daylight Angles of View when he worked for Polacoat down in Baltimore. And I have his complete collection of newsletters. And he got into things like geometry, and he got into things like rear projection and front projection and angles, but he did a very, very interesting angles of view, November 98, talking about brightness, contrast, and he mentioned 50 foot Lamberts is a practical upper limit for displays in a darkened room with high contrast. That's 171 candles per square meter. I don't know where he got that number from, but he did reference in the article. This is something that I guess was under study at the time by Smpte. Nobody at Smpte seems to remember it. So is that too bright in a movie theater where we can really crank up the brightness? Well, during a test a few years ago, I saw a 3.3 millimeter pitch video wall in a large darkened theater down in Texas with just dim footlights and sconces operating. Some viewers did complain of eye fatigue. The peak luminance for some of the test footage was only 200 candles per square meter, which is 58 foot Lamberts. But those viewers were sitting 40 to 80 feet from the screen. They had a very wide field of view. So where does field of view come into play? These two screens have identical luminance values. All I did was change with my camera the field of view, and I used the auto iris function to drive this point home. So at a distance, the screen may appear brighter as the iris opens up to see surrounding shadow detail. But as we get closer to the screen may not appear as bright as our iris closes down and surround shadow detail is lost. And the objects reflecting light are more noticeable with a wide field of view, but they're not as noticeable with a narrower field of view. So here at a Samsung press demo, much of the light in the space is coming from that LED wall, which I was told is running in excess of 1,500 candela per square meter. However, we have a lot of indirect sunlight coming in through the windows. The room is surrounded by floor-to-ceiling glass, and we have some room lighting on. So the limiting contrast ratio in this particular case is definitely under 15:1 to darker areas in the room. However, the display is definitely bright enough. At 15:1, we can clearly see the details in the picture. There's no eye strain due to high ambient levels. And even with nighttime footage, we can make out what's going on with this display. So it is bright enough for the room. But in another room, they were showing a high luminance display for the home. I don't know how many of you have an organic light emitting diode TV and OLED TV. I do have one. They can achieve about 700 candelas per square meter, small area brightness, and typically with average content 130 to 150 for a full white screen. LCD TVs with dense mini LED backlights or quantum dot arrays for high dynamic range can achieve 1,000 candelas per square meter with a full white screen. They're not limited like an OLED because they're not going to burn out. Inorganic LED TVs can push those peaks far beyond 1,000, but the thing is, can you watch a screen with average picture levels of 100 to 300 candelas per square meter for sustained periods in a dark room without eye fatigue? Well, we're going to find out. Higher luminance levels are necessary for displays of HDR content, but they're not for sustained viewing. So in another room at the Samsung demo, they showed their 0.84 millimeter pitch wall inorganic display. At the time, it was just about $300,000. A bargain if you've got the money. Measured 6 foot by 10, 12 feet diagonal. They said the full brightness, specular or diffuse white, is 1,600 candelas per square meter or 468 foot lamberts. That's easy for an LED to do. Average picture levels 100 to 300, 29 to 88 foot lamberts. Well, some viewers that went in this room said the images were too bright to view comfortably at viewing distances of 8 to 10 feet with the lights off. So we had the lights on, no problem. We had a very low contrast ratio, but we were well in excess of 15:1. But when we dimmed the room lights, totally different story. It was really difficult to watch HDR video from this display for a long period of time. In this particular cinema clip, they had outdoor sequences with very bright backgrounds and lots of white and off-white luminance values that had way too much glare at times. There was enough light to take notes. You could actually write while you were watching. And I was in there with Joe Kane and a few other people, and I put sunglasses on. They're kind of laughing, and then they did too. And I said, you know, I need them. It's too bright. It's painful to watch. Here's that cinema demo that I mentioned. 2019, I was at Samsung's Onyx LED cinema wall demo in Richmond, Texas. This is one of 2 theaters that has this wall built in. 46.2 feet wide by 25.9 feet tall. Resolution is 4224 by 2160. So it is a true 4K cinema wall. Full white can easily exceed 1,500 candelas per square meter, which is 439 foot lamberts. I don't know what inspired me to bring my spot meter, but I did. And they ran sequences of different video clips for us. They ran some ARRI HDR sequences, which were close-ups of faces on white backgrounds, just headshots. They ran some movie clips that had very, very high brightness whites, peaking at 200 candelas per square meter. When they showed the ARRI sequences, we were in 171 candelas per square meter, which is 50 foot lamberts. At that point, you don't need house lights. And to give you an idea, if you want to do that with a projector, you'd need 60,000 lumens. As far as I know, nobody makes a 60,000 lumens projector. You'd have to stack them to get to that brightness level. And probably a very inefficient way to light up a screen. An LED is just simpler. To give you an idea just how much light spilled off the screen with all the room lights off, here we go. Okay, this is no trick in exposure or anything. You notice on the wall, there are acoustic wall treatments and speakers. The chairs lit up, the tables lit up, the people lit up. So you don't need any footlights. This is one of these high-end theaters, by the way, where you order from a waiter and then they bring your food to your table and your drinks to your table. So they have to have some footlights, have to have a little bit of light in there. But at this point, the room is as bright, if not brighter, than if we turned on all the overhead lighting. I measured the light off this guy's shoe next to me, and it was 10-foot Lamberts. So that was pretty bright. It's a luxury theater with food and beverage service. We can't make it completely dark for practical and safety reasons. So with high luminance content, it was very bright. It was easy to see other audience members, trays of food, water bottles, and drinks. Very distracting. You could see all the people around you. If somebody's having a conversation or on their phone, you think that's bad enough in a dark theater. Wait, you see it in one of these things with everything lit up. So this got me thinking, was Kim Milliken right about that 50-foot Lambert limit? Because here we are at about 50-foot Lamberts. And we're in a room that has dark carpeting, dark walls, dark ceiling. It has blue seats. They're not really dark. They're dark blue seats. But yet we can see pretty much everything. We can see the people. We can even read. I briefly took out something to see if I could read by this much light, and I could. And that brings me to the last part of my presentation, which is just how bright does a television need to be? Well, consumer televisions today are easily capable of achieving 300 to 400 candles per square meter full white. That would be LCD. OLEDs can't do that. They can only do small area, about 700. And the LCD TVs typically 800 to 1,000 candles per square meter with HDR. OLEDs are more in the 150 to 170 range for full white, do automatic picture limiting circuits, so you don't burn out the OLEDs. And with small area, it would be 700. So those are absolute values. That's kind of like saying, what's the peak horsepower in a car? That's great, but if you can't drive it that fast, what good is it? How do those levels impact immersive viewing at night? Well, this LG OLED, a 55C9, is calibrated. I ran some tests over a year ago with portrait displays. They have a very unique system where you do this over an internet connection. And basically, they have access to the lookup tables within the LG OLEDs. LG gives them access. So you connect to the television through an internet connection. You set up your meter. You set up your computer with your test software, and you start it and walk away, and it calibrates itself. So it's making adjustments, then rereading, and making adjustments and rereading. I draped the whole thing with black velvet too, so no outside light influenced it. So once it was done, 130 candles per square meter in ISF bright mode, 38-foot Lamberts with full white. Contrast to room ambient and daytime ranges from 2 to 1 to 10 to 1. That might not seem all that bright, but it is when you watch it. Now at night, here we are at 130 candles per square meter. The only light in the room is coming from the TV. The limiting contrast ratio between this full white screen and the brightest surface in the room, which is the wall behind the couch, is 65 to 1. That's still not immersive. We need to be to 80 to 1. But again, you can almost read by this much light. This again is a full white screen, not something you'd normally be watching. So it's really time to rethink the process. As I said at the beginning, displays now have more than enough brightness for any application. That's not an issue anymore. If you need it, we can generate it. But as you've seen, a display can indeed be too bright, particularly for immersive viewing in darkened rooms, creates eye fatigue over time. I'll mention as a sidebar here that I was involved in a project a few years ago where we were in a very large theater testing out an LED wall. And the LED wall was running at maybe 150 to 200 candles per square meter with a variety of content. And we were sitting in a very large theater, some distance away from it, a good probably 50, 75 feet. And as the content was going by, we were seeing bright things on the screen. Some people next to me said, that's too bright, I can't watch that. My eyes are starting to hurt. So there is plenty of empirical evidence for this. A peak full white luminance level of 171 candles per square meter of 50-foot Lamberts for cinema viewing is indeed bright enough per Milliken. I don't, again, know where he got that number. I've not been able to find any reference to it in any Smpte research, but based on the tests that I did, I would say, yeah, 50-foot Lamberts, both in my home theater and at that LED cinema down in Richmond, Texas, is plenty bright enough. So what we need to do is determine our target contrast ratio first for the viewing environment, then calculate the required luminance or illuminance level. And I'm going to tell you right now, it's going to be very, very difficult to get much above 50-foot Lamberts and maintain a very high contrast ratio because of light spill. You'd have to pretty much drape everybody in the room with black, have black seats, have velvet on the walls, turn off all other ambient lighting, including the footlights, to get well over 101 contrast ratio. It's just not easy to do. Now, again, improving your limiting contrast ratio is involving changes to the viewing space, not by simply cranking up the screen luminance. So that really is what we want to think about, is what's the contrast ratio? How much reflected light do we have in the room? How can we improve the reflected light if we want to become immersive? Or do we put light absorbing surfaces in? Maybe that's the way to go. Again, a deep stipple black velvet will absorb an awful amount of light, but if anybody needs to move around in that room, it's going to be kind of difficult. They may be bumping into each other or tripping over things. And of course, in a practical application, you've got to be able to see so you can get up from your seat to go to the bathroom or get something to eat and drink and come back. And that's it. That concludes my presentation. So let's go back to the main hub here. I don't know if we'll have any questions, but I'd be happy to answer any if we do have them. Let's see. Okay, we did fix the mic, so that was one of the questions. All right. Any questions about what you just heard or saw? I know that this was a bit of a controversial topic at HPA, although it did come out of some discussions we had after the presentation that there is a recommendation that the peak luminance for a movie theater screen be somewhere around 100 candela per square meter, which is 29 foot Lamberts. I had not heard that previously. I didn't see a reference to that on any particular document, but if somebody can steer me to that, that would be very, very helpful. So, any questions? Okay. Guess, Tom, in the absence of questions, we can wrap things up.
I actually do want to ask you a question, Pete.
Sure.
So kind of in summary, is there a brightness threshold that you think is the most, useful? I know there's a lot of variables you talked about, all very good points, but is there a rule of thumb or anything like that? What brightness is too bright?
Well, I just gave it to you. It's the contrast ratio. Yeah, the easiest thing to do, because trying to determine what is too bright or to lay down a hard and fast rule and say that display is too bright. Yeah, a 3000 nit LED wall in a darkened room is too bright, but it's barely bright enough outdoors in a football stadium. So you can't work that way. That's what I'm trying to get everybody to think of.
Right.
The question to ask is, what's the contrast ratio that I need? Because those are easier to hang your hat on. And again, those rules that we use in the AV industry are not hard and fast rules, but they're just practical guidelines that we've developed over the years that we've calculated. 15:1 for a typical presentation, closer to 50:1 for analytical, and then 80:1 or better for theater. So all you really need to do is measure what the ambient light level is in the room in a theater, say with all the lights turned off, which is going to be very, very low, of course. And then you can determine how much light you need on the screen, but keep in mind that your screen is going to reflect light back in the room, which is going to raise your ambient light level. So I've kind of done some of that homework for you by saying that at 50 foot Lamberts, that's a pretty bright theater. So the only area where we might actually reasonably say that something can be too bright is in a movie theater, a darkened movie theater. 50 foot Lamberts probably is about as bright as you can get, because even with dark wall treatments and dark furniture and allowing for people wearing different kinds of clothing, bright or dark clothing, you can't, as you start cranking up the illuminance beyond that, all you're doing is making the room brighter and you're degrading the contrast ratio.
So does HDR change things? Because what's white is white there is different than everything else we've seen before.
Well, with HDR, people have to understand something about HDR. HDR is not full white, okay? HDR is specular. It's peak whites. So it's more of a logarithmic function. You might find that for average viewing, as I did in my theater, 200 is plenty for home, watching at home during the daytime, 200 nits. I'm watching it like 130 to 150. But if I'm watching HDR content, there may be a scene in the HDR content where something is hitting, let's say, 800 nits, 900 nits, 1,000 nits, or 500 nits, or 600 nits. So it could be a movie where somebody walks in front of a neon sign, or there's a bright street light, or you see a car drive by at night with a bright light, or you see a starburst, or you see part of the sun. But you'd be surprised if you take the average white level of content that you're watching, HDR content, you're going to find it's not up in the hundreds of nits. It's down in the lower range. It's going to be anywhere from probably 70 to 100 to 120 to 130 nits, maybe 150 nits.
Wow.
And that's what I actually measured was I was watching both HDR content from Amazon and also things like The Price is Right during the daytime, and then all on my TV. So the peak stuff can be 8 to 10 times as bright, but the average picture level is still going to be pretty low. So if you were to take one of those displays I showed earlier, one of those outdoor displays, which is 700 nits or something, or even 500 nits, and you put that, turn that on, you're watching TV, after a while, you're like, ah, turn it off, can't watch, it's too bright, my eyes hurt, it's way too bright. And then again, that also depends, it also depends on your field of view too. You have to take that into consideration. So if you're sitting quite a distance from a very bright screen, the effect isn't as pronounced if you're sitting very close to a very bright screen.
We saw that a lot when editing with Avid Media Composer and plasma screens first came out. You had these big plasma screens over top of your consoles and equipment, and all of a sudden you got fatigue and all kinds of things going on because that thing was just too bright.
Yep, exactly. That's my point precisely. I just shut off the AGC on the camera. So it's not a simple way to answer the question. So as I said, it depends on your targeted contrast ratio, it depends on the ambient light levels, and it depends on the viewing environment, how close you are to the screen, how far away you are from the screen, what are you trying to achieve? Obviously, you want a very high contrast ratio with as much neutral gray reflected light as you can in a viewing environment for doing post-production, especially color correction, because any of that ambient light is going to influence what you see in the colors. You know, your eyes are constantly being tricked by things like that. And there are Smpte recommendations, specific recommendations for a viewing environment for post-production, including having a gray illuminant that matches the target color temperature of the display you're using in the room that's pretty low. I mean, it's going to be probably like 15 to 20% of the light level of the screen, so that you're not in a completely darkened room. The reason they do that is in a completely darkened room, working, let's say, a reference monitor that's at 100 nits, after a while, you're going to have eye fatigue. Your eyes are going to start to hurt. So you need some light because your eyes trying to figure out what's in the dark areas that I'm not seeing near the screen. Well, if you bring it up to a low level and your iris adjusts and there's not as much eye fatigue, but that low level is a neutral gray, matching your color temperature, so that doesn't affect your color decisions. So yeah, field of view, ambient light, contrast ratio. And what'll happen is as you do all of that, you'll just magically arrive at the brightness level. And it's funny because I've done this at seminars for AV guys, and they're going to say, how did you know that I needed exactly 6,000 lumens on the screen? I said, I just backed into it using these numbers. I said, there's no reason to guess. Why put a 10,000 lumen projector in a room if you find out a 5,000 lumen projector is going to do the job just as well? There's no reason for it. You know, your client's paying extra money for something that they don't need.
Yeah. And that's modern. Years ago, I worked at Jefferson Hospital, and we were doing ultrasound in a big, convention scenario. And back then, you couldn't get to these light levels. So the brightest projector and the biggest image was what they needed because it was all black background with white detail, and in a darkened room. But today, we have the luxury of high brightness.
Well, and the other thing that you all need to keep in mind here is that the display industry is undergoing a fundamental change, almost revolutionary change. And that is that it's all heading towards some form of light emitting diode generated imaging, whether it's organic light emitting diodes or inorganic light emitting diodes. This is clearly where the display is going. And over time, we've swung back and forth between reflective imaging, which is movies and lantern slides, to emissive imaging, which is a CRT, to reflective imaging, which is brighter movie screens, and then transmissive imaging, which is LCDs, and then emissive imaging again, which is plasma displays, and now OLEDs. But ultimately, it's all going to be emissive displays because we can make them super thin, we can even fold them, we can make foldable phones out of them, we can wrap them around things. So now we can make the display do whatever you want it to do. And personally, I think that you're going to see at some point, once the prices come down and we have more reliability and stability in light emitting diodes, you're going to see more and more movie screens move away from projector and screen to a one-piece emissive solution. because it's a lot easier to generate the photons with an LED than it is with a projector, especially if you're going to do things that require 3D glasses or applications where you have to wear some kind of eyewear, virtual reality, whatever it is, and you're having light loss. Well, the easiest way to make that up is with an LED. So that tells you right away, we're already venturing into the realm of having displays that are bright enough, if not too bright, and we want to dial back the horsepower. So, you know, LEDs eventually are going to take over everything. The wall that you saw from Samsung, they've now introduced in the last year cheaper versions of it. They're only $100,000 for a 110-inch display. But everybody's going in that direction. LG has come out with a roll-around one for classrooms. Sony's working on similar projects. The Chinese are working on it. So eventually that stuff's going to migrate into a television. You're going to have micro LED televisions. You're going to have micro LED smartphones. You're going to have micro LED smartwatches, laptop screens. You're going to have outdoor digital signage. It's all going to go to micro LED. We're a ways off from that. I predict by the end of the decade, you're going to see it in widespread use. But clearly, using that technology, we'll have displays that are obviously way brighter than we need them to be, can certainly keep up with what our demands are. So I suggest everybody just forget about brightness, assume you can find it somewhere, and instead calculate your contrast ratio, taking into account the ambient lighting levels that you're going to have in the room and the field of view that you're going to have in the room, and then arrive at a targeted contrast ratio for what you're going to do. And then that number will just fall very easily into place. And it's going to be, again, foot Lamberts, candles per square meter, because it's going to be illuminance. It's not going to be projection off a screen. I'll see more of that. I am going to be going out to CES. I did decide to make a trip this year. So I will be out there for 2 full days of the show. And I expect to see a lot of demos of inorganic LEDs and some advanced applications for OLEDs and other technology. So I'll have more to report on back next year.
As you reviewed so many of those different technologies, reflective, emissive, and so on, it made me think of all these numbers are when you first set up the display, but age. Are any of these, I know you've talked to us about this years ago, but any of these degrade faster than another?
Well, OLEDs definitely do. There's no question about it. And there's all kinds of circuitry built into OLED TVs and OLED displays to extend their life, because organic light emitting diode materials all have different aging. They have different life cycles to half brightness. And the critical one is dark blue. Just as dark blue phosphors were the first to go with CRT TVs, and dark blue was the first color to go on a plasma display, dark blue is a very unstable material. And nobody's really been able to get it much past 5,000 hours to half brightness. However, we are able to get the displays brighter. So that's the limiting factor with OLEDs. Now with inorganic light emitting diodes, you don't really have that issue. A blue LED is going to last as long as a green LED is. A red LED is going to last as long as the yellow LED is. But you have to keep in mind that LED displays, inorganic LED displays, don't work the same way as other displays do. They more resemble plasma displays in operation. That is, they're switched on and off at very high rates of speed, because if you were to take red, green, and blue LEDs and fade them up, or raise the voltage slowly to increase the brightness, you wouldn't be able to plot a gamma curve. It would be wandering all over the place. So when we run LED walls, we run them at full brightness, or whatever rated brightness we want to run them at. It may not be full brightness. They may be capable of 3,000 nits. Maybe we say we want to run them at 1,000 nits. But once we set them there, we switch them on and off very fast, typically about 2,000, 3,000, 4,000 times a second, using pulse width modulation. And with pulse width modulation, as we've seen with plasma and DLP, it's very simple to create multiple gray levels. And with 10-bit and 12-bit addressing, you can get very smooth gray ramps out of them. Your eye can't integrate the on-off cycles fast enough, so it just appears that the display is dimming or getting brighter or changing color or whatever it's doing. You don't see those on-off cycles. Your eye can't adapt that quickly. And that's basically why the LED is so attractive. There remain issues with color. They have to batch LEDs. They manufacture a whole batch at one time. Those all go into the same display. When you replace display modules, you have to worry about matching colors. So there's a lot of obstacles that have to be overcome with LEDs, but those obstacles are being overcome. We're able to get them smaller. We know we can make them last a really long time. I mean, you'll replace the display before the LEDs ever reach any kind of half brightness. And of course, they don't run at fairly low voltages. And running them in PWM mode conserves a lot of energy, because if you didn't run them in PWM mode, you'd burn up a lot of electricity, which, as an interesting sidebar, is a problem with some of these 8K TVs that they've come out with that have full array backlights to do HDR. They're actually exceeding the Energy Star, and in fact, some of the EU regulations on energy consumption, because you have so many pixels on an 8K TV and you have full array backlights with thousands of diodes. Well, you can imagine what's happening. I think I saw an 85-inch 8K TV had a power consumption of something like 470 watts, 450 watts, which is an awful lot for a, that's like plasma territory. That's where plasma was many years ago. But getting back to the main point, the LED is going to be it. It's whatever your display is in the future. I hope I'm around to see it. It will be some form of LED. It'll be micro, mini, organic, inorganic, but it will be some form of LED. It'll be emissive, and it will be plenty bright enough.
Very good. Thank you so much, Peter. That's tremendous. Does anybody else that's on the call have a question? You can unmute yourself and jump in.
Just real quick, Pete, this is Derek. Good to see you again.
Yeah.
Any comments about the old concept of bias lighting? It seems like that's pretty worthless now, or is that still a valid thing to consider?
You're talking about LED lighting on a live set?
Now, more from behind the TV to get the colors neutralized, or to give you less fatigue if you have bias lighting to bring the ambient light up.
Oh yeah, no, there's well, yeah, that's a Smpte recommendation. It's not generally not recommended that you watch television in a completely darkened room, which, as you saw when you saw my TV lit up at night full white, it isn't a completely darkened room. There's quite a bit of light spilling off the walls in that room. So yes, they do recommend that you have some sort of bias light when you watch TV. In a movie theater, obviously they don't want you to have a bias light, but you have it. You have footlights, you have the exit signs. I mean, you have some bias light. And again, if you make the screen bright enough in certain sequences, you're lighting up the whole theater anyway. So you really don't have a bias light issue there. The bias light really comes into play more with critical applications. So I'm going to put color grading and exposure grading in immersive. Good luck hitting 80:1. They're not going to do that with a bias light, but that's, again, we'd love to have 80:1, but if it's bright enough, your eye's going to have fatigue at 80:1. So that might not be a very bright display. It might only be 29-foot Lamberts or even less, if you can get the room really dark, because again, your eye is constantly irising to adjust for the brightness level. So yeah, bias lights are still a good thing. I recommend them. I recommend leaving some light on in a room when you're watching TV. If you want to be a nitpicker about it, you can match the color temperature, whatever the TV is calibrated to. If not, you know, any light in the room will help. But yeah, it's all really to relieve eye strain. By the way, there's going to be a paper in the Smpte conference on a very unique method. I can't talk about it, but very unique method of calibrating LEDs to make them more accurate, that you might want to, if you're going to the conference, you might want to check in that paper. It's pretty clever, because some of you know now that green screens are being replaced by LEDs. There's a lot of productions that are being done. The Apollo 11 movie a few years ago, all those sequences shot, you know, flying in through space, through the clouds and everything, all that stuff was shot against an LED wall. There was no green screen involved. And there's ways that you can do parallax correction and dial it into the imaging on the screen, so as to change the point of view of the cameras. The point of view on the not a green screen, the LED screen behind you also changes, and it looks pretty cool. And you can get the pitch down. If you get too close to it, you'll see the pixelization. You'll see kind of an interference pattern, a moire pattern from the LEDs. But there's some really interesting work being done with that. All right.
Okay.
Yes, Mandalorian does the same. Yeah. And I think we've reached the end here.
Thanks, Pete, for a great presentation. A lot of information there on that. And I do want to add the other thing that I think is important, and this was going back into the 90s. It's content, what content is on there. Because if you're putting spreadsheets up, it's a whole different ballgame than if you're doing video or HDR. So I think that comes into play too when you're figuring out what type of projection you needed.
Right. Well,
even
keep in mind, again, you can read a book with 7 to 1. You can read a newspaper with 7 to 1. It's
Yep,
black text
so-
on a white background. So yeah, that's why those recommendations came out, that it's very easy to achieve a 15 to 1 contrast ratio in a room with, you know, conventional fluorescent lighting or some of the newer LED lighting and a projection screen. You need a lot, as I said in that example, I needed a 6,000 lumen projector to do it, but I'm at 15 to 1, and I can very clearly see what's on the screen. I can read the information on the screen. It's not a movie. It's not trying to entertain me. It's just, you know, it's just a meeting.
It's just a meeting, yep. And I've done that several times where you're turning back the brightness of the projector just because of the presentation. It's just spreadsheets or something that you don't need a lot of brightness. So again, excellent presentation. So thank you everyone for showing up and watching it. And this will be available online in a day or so. So I do see we have one other question over here. Yeah, with Thomas Michaels, Mandalorian production does the same. So thanks again, everyone. Thank you so much, Pete, and we look forward to future presentations from you.
All righty. Thanks everybody for coming out.
Thanks, Pete.